Okay, so what I would like to talk about now is the LP convergence of Fourier transforms. And really what I mean is whether or not we have any kind of LP version of Fourier inversion. Now this is a bit tricky and it's harder to even pose the question for the Fourier transform than it was for Fourier series because it's not even clear how to define the Fourier transform. So when P is between 1 and 2, then by the Hausdorff-Young inequality, the Fourier transform makes sense and it's an LP prime function. But for P bigger or equal to, for P bigger than 2, it's not clear how to even define the Fourier transform. Okay, so what we're going to do is we formulate Fourier inversion in a way that is fairly trivially true for L2 functions, basically thanks to Fourier inversion, and allows, basically is a reasonable question to ask for LP functions, P bigger than 1. So in particular, let's just take f and let's cut off by this characteristic function. So this characteristic function here, well, this is just the usual Euclidean ball centered at 0, radius r. So it's just all x and rd, where the absolute value or norm of x is less than r. Okay. Let's say fr is this truncated, this function f, but cut off to this ball. Okay, so we claim that if I take this fr, take the Fourier transform, multiply it by the characteristic function of this ball, let r go to infinity, then we get f back. And this convergence is an L2. And this is really pretty easy thanks to Fourier inversion and the isometry property of the Fourier transform in L2. In particular, we can just write f as the inverse Fourier transform of the Fourier transform. That's just Fourier inversion for L2 functions. Okay, so really, this minus f is exactly what we have here. The inverse Fourier transform is a isometry on L2, so we can get rid of that. It's linear also. Now we can just add and subtract the characteristic function times Fourier transform. Let r go to infinity, and both of these are fairly easily going to go to 0 in L2. So let's just do this one here. Well, so clearly I can factor out the characteristic function and pull it out. So this is less than or equal to f minus f, fr minus f, whole thing. Fourier transform again is linear. Well, this is just fr minus f L2, and dominate convergence, because f is an L2, says that this goes to 0 as r goes to infinity. And this is very, very similar. This is just dominate convergence theorem using the fact that the Fourier transform is an L2 isometry. All right, so the beauty of this little lemma is that, well, if f is an LP, then by Holder's inequality, fr is an L1. Just use Holder's inequality here. LP, you do P, it's LP norm of f, LP prime norm of this characteristic function, which is finite. Okay, so fr is an L1. That means a Fourier transform is trivially well defined. I mean, there's no issue there. It's actually given by an integral, and it's in L infinity. So if I multiply by this characteristic function, we have an L infinity function that's supported on this ball of radius r. So that is in any L Q for all possible Q. So in particular, when I take the Fourier transform of this whole thing here, well, by the Hausdorff-Young inequality, it is actually in LP for all P bigger or equal to 2. Okay. So including it's in L infinity also. So the bottom line is we know something about the inverse Fourier transform of what I just circled. I think I said the Fourier transform. I meant the inverse Fourier transform of what I circled. Okay. So it's reasonable to wonder and to ask, because this, the inverse Fourier transform of this is, it is in, as I mentioned, it's an LP for all P bigger or equal to 2, thanks to the Hausdorff-Young inequality. It's reasonable to ask this question for LP functions. Okay. And the answer is, surprisingly, yes, for P bigger than 1, if D equals 1, but no, if D is bigger than 1. I say surprisingly, this part is not surprising. It's very classical that in dimension 1, we have this kind of version of Fourier inversion for LP functions. But it's surprising, and I'll talk a little bit more about this in the next video, that this is false in higher dimensions. Okay, so let's kind of start getting into how we prove this. So an easy homework that I could have assigned many videos ago, it's really just a very easy use of Holder's inequality in a way that we've actually done before. And implicitly, we've actually probably proved this already. This is called Young's convolution inequality, that if F is an LP, G is an L1, and here we're in any dimension, then the convolution is in LP, and the LP norm is just less than or equal to the LP norm of F, L1 norm of G. We're going to use this to prove the following variation of the homework problem that I assigned, and that is if F is an L2 and G is an L1, then the Fourier transform of a convolution is a product of the Fourier transforms. So if F is an L1, this was homework, so the trick is how to go from L1 to L2. So let's just see how to do that. And this might actually help for homework, actually. So the way we start this off, and the only way we can start it off, is let's write down what the Fourier transform of F is. In particular, proof. So let's say Fn is an L1 intersect L2. And let's assume that Fn converges to F in L2. Okay, then that means that the Fourier transform, by definition, is his limit here, and it converges in L2. Okay, so what are we going to do? Well, let's compute this here. Let's see what this is going to be. Well, So because we have convergence in L2, so first of all, I should mention that G is an L1, so the Fourier transform is an L infinity. F is an L2, so the Fourier transform is an L2. There's no issue with this product. It's a product of an L infinity function and an L2 function, which is L2. So because we have, so we have this convergence in L2, so that means that we have this convergence here, that. So in L2, we have that these two are going to be equal, fairly trivially. Okay. So let's figure out what this is. Okay. Well, so by the homework, we know what this is. Fn is an L1, G is an L1. So by the homework, this is going to be Fn convolved with G times a Fourier transform. That's just what these two are equal to. Okay, right, so I claim this converges to F convolved with G Fourier transform in L2. So let's just see that. Well, so actually, let's do it this way. Yeah, so, right, sorry about that. So let's actually do look at this here. Okay, so first of all, G is an L1. Fn is an L2. So from this Young's inequality, this is an L2. This whole thing is an L2. So I can use Fourier inversion because this whole thing here is an L2, Fn convolved with G. Okay. Well, this is going to be Fn minus F convolved with G. And by Young's inequality, yet again, this is Fn minus F. So remember, we just used Young's inequality to get that this here is in L2. So I can use the Fourier inversion. Okay. And again, as we've used implicitly a million times, Fourier transform is linear. So this is the L2 norm of Fn minus F, L1 norm of G by Young's inequality. Well, as n goes to infinity, this converges to 0. So Fn convolved with G, well, we just proved, sorry, there's no limit here. This is F convolved with G Fourier transform. Okay. Well, it doesn't really matter that it's an L2. These two are going to be, well, this means that these two, we have two, so these two are equal in L2 and hence equal almost everywhere. And that's exactly what we wanted to prove. Okay, so let's put this to good use. So let's say SRG is this characteristic function of the ball times Fourier transform of G inverse Fourier transform. For G in L1, let's get a nice concrete realization of this. So we're going to basically do what we did for, or very similar to what we did for Fourier series, or at least in spirit. Okay, so first of all, this is a perfectly fine L2 function. So Fourier inversion holds. Okay, so what do I have here in the box? Forget about this inverse Fourier transform here for the moment. I have the product of these two Fourier transforms. Okay. So, right, so G is in L1. So G is in L1, F is in L2, F being the inverse Fourier transform here. So this is really F hat G hat, and we know it's the Fourier transform of F, which is the inverse Fourier transform of this characteristic function convolved with G. Okay? Well, let's use Young's inequality, Young's convolution inequality one more time. So this is obviously a very powerful inequality. So this is an L2, the inverse Fourier transform of an L2 function. This is an L1, so the convolution is an L2, and hence Fourier inversion holds. Okay? Now the beauty here is that, yes, this is an L2 function, this characteristic function, and hence the inverse Fourier transform is L2, but this is also L1, so the inverse Fourier transform is just an integral, period. So let's figure out what it is, at least in dimension 1. So everything I did is fine for dimension whatever. So in dimension 1, we can figure out what this is fairly trivially. So this obviously is going to be, well, integrate over the real line, characteristic function, minus r to r in dimension 1. E, because it's inverse, it's no minus here, 2 pi I x dot u, or xu du. There is no dot here, it's just ordinary multiplication. So this just becomes integral minus r to r of this exponential here. You can compute this very easily. And yeah, and this whole thing here, well, this is just sine 2 pi rx. So it's sine 2 pi rx over pi x. And because this is very similar to the Dirichlet kernel, there it was sine 2 pi n plus 1x over sine pi x. But sine pi x and pi x near 0, near the singularity, are basically very similar. But because this is so similar to the Dirichlet kernel, we often call this also the Dirichlet kernel. Okay. Okay, so in other words, SRG, at least for G in L1, is just convolution with the Dirichlet kernel, and hence is given by this integral operator. Okay. So just a note that we can get a good, we know something about SRG. In particular, it's at least an LP for any P bigger than 1, as long as G is an L1. Again, by Young's convolution inequality, we have the following here, and I'll leave it as an exercise to get that the LP norm of this Dirichlet kernel for P bigger than 1 is bounded. It's finite. It's really not that hard. Yeah, I mean, it's because there's really it's a removable singularity at near x equals 0. I mean, just L'Hopital's rule, it's going to be, I think, as x goes to 0, I think it's just r, or maybe 2r, whatever. But yeah, away from 0, the integral is convergent as long as p is bigger than 1. So really nothing to this fact that this is finite. But anyway, okay, so rather remarkably, I'm going to claim, and this is just because of the very concrete nature of this operator. And this happens a lot in PDE and harmonic analysis and different areas of analysis that, happens, it definitely happens in the theory of holomorphic function spaces, with the Bergman projection, the Hardy space projection, that, we have a very concrete integral operator, and we can read off properties of this integral operator because it's such a concrete object. So I claim that we can get an LP bound, an operator norm bound for SR independent of R. So let me expand on that a bit. So let's just look at this LP norm. So here I'm just going to change variables and write it as g of x minus y sine, or g of x minus y times dr of y, like I can always do with convolution. Okay. So let's do a change of variables. And I'm not going to do different letters just because we're going to do this for x and y, but if you want to, you could. Yeah, so we're going to let y go to y over r. That's going to get rid of this r here. And there's no r, 1 over r outside, because when we change the pi y, or change the y in the bottom, it's going to cancel the 1 over r. On the other hand, if we let x go to x over r, we do get a 1 over r. Okay. And well, because the r went away, it's basically like r equals 1. So this is really S1, SR applied to this function here when r equals 1. And here G, well, this is fairly self-explanatory, but whoops, sorry about that. So dump in x here, that's just x over r. Okay. Well, let's assume that I have an operator norm bound from LP intersect L1 to LP for S1. I mean, here we're only considering G as an L1 intersect LP, because we want to study this on LP, but we don't really have a good concrete realization unless we're dealing with L1 functions. This whole Fourier transform of a convolution is a product of Fourier transforms. We needed G to be L1 for that to work. Okay. All right, but you do one last change of variables. This is just the LP norm of G. Okay. And this operator norm is just the usual operator norm. If there's any confusion on what the norm on LP intersect L1 is, it's just the LP norm. Okay, right, so let's put this to good use to improve the following lemma. So for any dimension, the answer to our question is yes, if this bound here is finite. Okay. So what's the proof? Well, let epsilon be positive. Let's pick some Schwartz function where f minus phi, this Schwartz function, is less than epsilon over 1 plus Cp, where Cp is this operator norm here. Let's look at this lim sup here. Let's add and subtract 3 terms and use triangle inequality. Adding and subtracting SR applied to the Schwartz function, and adding and subtracting phi. Okay. Well, so it's going to be a fairly straightforward homework that as r goes to infinity, so this converges to 0 as r goes to infinity, and this shouldn't be too surprising because remember what SR is. By definition, SR is the following, and if we have a Schwartz function, it's reasonable to think that because the Schwartz function is so nice, it's C infinity decays faster than 1 over any polynomial in modulus, that we can let r go to infinity. This characteristic function formally becomes just 1, and so Fourier inversion should kick in. So as r goes to infinity, at least applied to a very, very nice function, it's reasonable that we get the function back. And it's not hard to prove using the very, very nice facts about Schwartz functions. And I'll leave that as a homework for the next homework. Okay, well, right, so for this one, so this whole thing here is going to be SR applied to FR minus the Schwartz function. And remember that F is an LP, and hence you multiply by the characteristic function with radius r, center 0, FR is an L1. FR, again, is just, well, it's the same thing as F, just multiplied by this characteristic function. Make that a little neater. Actually, I can barely even read that myself. So yeah, FR is characteristic function. So FR is an L1. So so both of these, so it's an L1 intersect LP. This Schwartz function is clearly an L1 intersect LP. And we know that in LP norm, this is less than or equal to the LP norm of FR minus phi times this CP here. That's what we just did up here. Okay, so, well, this is just less than epsilon over 1 plus CP. Now, by Dominant convergence theorem, this whole limit here is going to be equal to CP F minus phi LP, well, plus epsilon 1 plus CP. And that's less than, well, epsilon, because this is less than epsilon over 1 plus CP. So again, Dominant convergence theorem says that this is going to be equal to, in the limit, F minus phi and LP. Okay, so I will end this video here, and in the next video, I'll discuss an example to show that things are pretty miserable no matter what dimension we're in when P equals 1. And in particular, S1 doesn't even map L1 intersect, S1 does not even map L1 into itself. Okay, so we don't need sorry about that. I didn't mean to write intersect L2. So yeah, and in particular, a very slight modification of the example I'll discuss gives you that SRFR is not even an L1 necessarily. So that you can cook up a function where SRFR for any R is not an L1, so this question doesn't really have much meaning. Okay, yeah, so that'll be in the next video. And do hand in homework soon, please. I'll give homework back to you in the next day or two. So yeah, stay tuned for a new video. And I should mention where this is all leading to is we're going to study, and we're going to need to study the boundedness, LP boundedness of the Hilbert transform, which will really be the main focus of the rest of this course. We'll develop the very powerful tools like the Hardy-Littlewood maximal function, Calderon-Zygmunt decomposition, things like that, to study the boundedness of the Hilbert transform, which will give us the boundedness of S1. And that's exactly what we'll do in the next video. All right, so so long, take care. New video coming soon. Bye-bye.